group of Pavia. And he has a long tradition of activities on simulations. So since 1990, he got a professorship first at the University of Dortmund and then at the Technical University of Munich, where he held the chair for computational engineering. He was also very active because he was also the vice president for research of TUM. And he was one of the founding director of an international graduate school of science and engineering. And I could say that if he is active on additive manufacturing, for all of us that are active in additive manufacturing, means that, you know, there is a lot to do, and it's a very hot topic, because due to your experience, you know, if you believe in this technology, we are glad that you are active in this. So Professor Rank is extremely well known for his research on numerical mechanics engineering, especially for high-order finite elements, immersed boundary methods, you know, integration schemes, and so on. And he got many awards, but I don't want to take, you know, too much time. And so really, thanks again, Ernst, for giving us the opportunity of this lecture. So you have the floor, and please go ahead.
Yeah, Ferdinando, thank you very much for this kind introduction, and thanks a lot for this invitation. I'm really very happy to be able to present here some of our work on this topic. As you said, it's really a hot topic. Well, not only in the melt pool of the laser, but also from the point of view of numerical simulation. I would like to concentrate today on, I think, in particular, one methodological problem, the challenge of the scales, which is involved in the simulation. And in particular, I will report on research projects which are or were conducted, are still undergoing research with my PhD students, Philipp Kopp, where also Victor Carlo collaborates a lot, and in the second part of Alexander Paolini, Nina Koshunova, who is a frequent visitor to Pavia, is also contributing to what I will talk about. Okay, just to give a little overview, I will just start to address some of the problems. Then I will concentrate on work which is in the center of the PhD project of Philipp Kopp, Space-Time Finite Elements. And I will try to show that this is a very interesting approach for process simulation in additive manufacturing. In the last part, and this will be the shorter one, I will then go to product simulation, talk about printed viscoelastic components. This is a little bit more from a practical and also from a civil engineering point of view, where these components may play a significant role. In this part, I will also use, well, immersed boundary methods, so our beloved baby in Munich, the finite cell method. And well, let me start with, I think this introduction is really not necessary in this seminar, so I have only one slide. Additive manufacturing is extremely promising. It offers large design freedom, a very complex geometry, but it also has a lot of challenges. I just mentioned two. Wherever the mechanical properties, and in particular the distribution of mechanical properties, are important, then we really have problems to solve. And the same, if the dimensional accuracy of a product is important, then additive manufacturing is in many situations not completely competitive with other manufacturing technologies which we are having. So there is still a lot to do, and I think the simulation can help a lot in it. Well, main challenges. And I will concentrate in my talk on laser powder bed fusion as a technology for AM processing, where it has to be said, of course, that quite a few other technologies for producing metal additive printed parts have very similar problems. Well, the problems there is multiphysics. We have evolving domains. This, I think, is completely clear from the process itself. I will concentrate on the right side of this slide, so on the spatial scales and also on the temporal scales, which are, from a simulation point of view, I think, as demanding in the temporal as the spatial scales. Well, let us look at one, example, which is actually the now already, I think, famous benchmark of the, why does it not run? Okay, now it's running. The AM benchmark, which was defined in 2018 by NIST and in collaboration with the National Institute of Technology. So most simple problem which we are having here. Looking at the scales which are there, so it's a small plate, 2.5 by 2.5 centimeters, and looking at the melt pool which we are having there, and looking at the dimensions, this melt pool is in the range of 400 micrometers in length and about 40 micrometers in depth. So this very simple example, one stroke only, one layer only, so one cannot really speak about on additive manufacturing or 3D printing there. Nevertheless, the difficulties already get visible for this very simple example. Well, what do we have if we look to the thermal problem only in this case? So I boil everything down to the most simple problems which we can address, but where we see all the problems. Well, if we want to follow the path of the laser, then, well, there is a rule of thumb that we should not have time steps which are larger than, say, the motion of the laser of, say, 1/8 or 1/10 or maybe 1/5, but this order of the melt pool length. So this is the physically motivated time step, move the laser by such a length, which would be about half of the diameter of the size of the laser spot in itself. Well, what does this mean? This shows that we go, well, at most 100 or 50 micrometers, meaning that for this simple stroke which we are having here, we need about 500 time steps for this one simple short stroke of 2 centimeters. Well, let's look at a little bit more complicated problem. So let's look at this square, which is hatched, again 20 by 20 millimeters, and the enlarged part shows now the scan strategy of the laser. So it goes diagonal, it starts up there in the corner or goes out in the corner, and then goes to and fro in the diagonal direction of this square. We already have, for this very simple problem, and again, it is only one layer, we have a laser path length of about 2.5 meters, meaning that for this we need 50,000 time steps if we really want to resolve the physics on the scale of the melting pool. Well, and I think it's not necessary to mention that a lot of the physics, of the important physics, happens on scales which are much lower, going down to the molecular level, but I only concentrate on this macroscopic level, so from the melt pool to the laser path. 50,000 time steps necessary by the physics if we want to resolve really what happens with the laser in this thermal problem. Well, looking again now at this simulation, and let's have a look at the corner where we either go out or go in of this structure. You see here a mesh refinement in this case. I will come back to this later. We see the dimensions, and one thing where I want to, which I want to mention, is if you look to the shape of the melt pool, well, it is not that easy as it was in the simple single stroke. So it is a really three-dimensional shape which we are having there, and this shows that the strokes, the different directions of the strokes, so this is here just around the corner, they influence each other, meaning that, well, of course, there are a lot of possibility to shorten the simulation by not looking at an individual stroke, but by looking at a full layer. And we can get, of course, a lot of information out of it, but to really simulate more of the physics and the interplay between the different strokes which we are having, we really should be able to follow the direction and to follow the path of the laser. Okay, so what does this mean? We need adaptivity. The general principle of adaptivity is we compute, we estimate something, we may estimate the error, or we may estimate other quantities to which we adapt. We extend or we adapt the space of approximation from the computational point of view. And we loop over this until some criteria is met, which allows us to stop the computation. So for the extension or adaptation in space, we have the well-known H version, meaning we refine or coarsen the mesh. We have the P version, we increase or reduce the order of approximation, or if we use isogeometric analysis, we may also have a combination like increase and reduce order and continuity. Looking at the time scale, and this is important, we have a spatial temporal problem. We have the possibility to also adapt the time step length, or we can adapt the order of approximation. So this is what is possible there. Well, please be aware, and I think this is important, we are talking, if we simulate additive manufacturing, we are always talking about 3 dimensions in space. So space and time means 4 dimensions. And this is exactly where I think a large challenge from a numerical point of view is we should have 4-dimensional adaptivity in space and time. And this brings me to this space-time finite elements, which we consider as a very interesting candidate, in particular, if we look to adaptivity. Well, for space-time finite elements, there is a long list of literature. It started already in the 1970s, and well, recently it has also gone, if one looks to the research of Langer, it goes to the isogeometric analysis. To our knowledge, there is not yet any really general software around which would be adaptive in space and time, so in this 4-dimensional setting. Well, I will try to show you some ideas and first results which we have in this direction. So let's look at a model problem, and to explain it, I start with the linear heat equation in one space dimension. So general formulation, as you see it here, what is used in most, I would say 99% of all cases in engineering applications, is the method of lines, meaning that we have a different approximation type in space and in time. So in space, for example, with finite finite elements for the spatial operator, so the Laplace operator, which we are having here, and finite differences in time. And well, you can use many schemes. I formulated here just the backward Euler. So that's standard. And this means if we draw the space-time grids which we are having here, a horizontal space, so one-dimensional, and vertical time, then we have, well, an ununiform, so an adapted grid, so just these elements which we are having here in one line, so at one time step, we are, in the simplest case, proceeding in equal length time steps we are having here. So which this means that we refine and de-refine with equal long time steps. Well, this is trivial in 1 dimension. It is already quite challenging in 3 dimensions. So refinement and de-refinement in 3 dimensions, this is something which you do not find in commercial codes until now. There are quite a few research codes around, but commercial codes, refinement and de-refinement is something which is very rare. Well, and still in this picture, in time direction, it is uniform, so no adaptation. Of course, we can now adapt also in time, having different lengths of time steps. So this is indicated in this grid, which we are having here. So in this range.
Ernest, I don't see, I don't know if it's just my problem, but I just see the equations on the left.
Okay.
Is it, I think there is, I don't know, Massimo, do you see?
Yeah, I was writing you that exactly this problem also from my side.
Oh gosh. Okay, so let me stop. That's astonishing. I see it.
Stop the presentation mode and maybe restart it, you know.
Yeah. I stopped the presentation mode, so 1 second.
It's an informal seminar, so we don't worry.
Yeah.
You know,
I have a problem with my.
It doesn't matter how many times we try, and you know how experienced we are. There is always the possibility that something doesn't go perfectly right. Almost.
Okay, so you saw the movies at the beginning. You did?
Yes.
Okay.
It took a little bit of time, but then we saw it. Yes.
Okay, so let me check now again. I have stopped my PowerPoint and started it again. So now you see the
Yes.
development mode, is it right?
Yes,
exactly.
Now we see the picture. Yeah.
Okay, so now let me. Okay, do you see still the picture?
Yes, now we do.
Okay. So there was some problem with my PowerPoint here, obviously. Okay, so now here we have the adapted grid, yeah, and well, what you see here is a typical grid of a local refined spatial problem. This is what we would have here, but this is different from the line adapted. And this one, which is still a kind of adaptation which we are having here, it has, of course, a few problems compared to what we really would like to have, like this one. If I compare these two approaches, well, here, either with the uniform or it would be the same with the time adapted, we have In parts which are out here, for example, you see my mouse here?
Yes, yes, we do.
Okay. In parts here, we have much too small time steps. Nothing is happening, and this would be far away from the laser in a sense. Nothing is happening. Nevertheless, we are having small time steps. This is different if you would look at this as space and time. So I have here coarse space and coarse time. So much more advantageous with respect to the number of degrees of freedom. There is another problem in this method of line, and this comes with high performance computing. Well, as you all know from the structure of this method of line, we can compute one spatial problem for one time step. Well, even if this may be rather large, if you have really a huge hardware, high performance computing, then this might be a problem which is too small to be really efficient for high performance computing. But if we look to the right side of this picture and consider this as a space-time finite element, then we have a different situation. We can make slabs. So meaning that the lower slab, the lower part, this is what we really solve once at a time. So this is a space-time problem, which is adapted in its size to the high-performance computer. And for the second time slab, the same. So we can adapt the size of our problem to the opportunities which are offered by the hardware which we are having. Okay, so now let's ask the question, is it possible, and how is it possible really to go 4 dimensions? Space 3 + 1 in time, 4 dimensions for a heat equation, and I will show it here for the linear heat equation, and we will then come to the nonlinear heat equation where you can go in the direction of additive manufacturing. Okay, so the linear heat equation, and if you look to the weak form, we do not make the method of lines, but we weight our equation with the use with the unknown function with shape functions w, which appear here as a weighting also for the time derivative. So this is one possibility, which is a standard Bubnov-Galerkin weak form. Another one, and there are many methods around, another one which we are investigating and which we are using, where you use instead of the functions for weighting the derivatives of the function, so that you get here a kind of symmetric term in the time derivative. This is then continuous for the shape function, so continuous Galerkin, and a Petrov-Galerkin in that sense that we have a different derivative in the weighting functions. Okay, so as I said, we want to go, and we really want to make the big step. We want to go adaptive in space, adaptive in time. We want to be able to make H refinement, and we want to be able to make P refinement. So the full register of all possibilities which we would like to have. What we are using is a variant of the multi-level HP refinement, how we call it. Well, what is the idea of it? First, look into the one-dimensional example. Lowest level, we have shape functions, linear ones, quadratic ones, cubic ones, and quintic ones in this case. In principle, in all 3 one-dimensional elements. So over the middle element, we take out the higher modes. We use an overlay mesh where we have again a similar ansatz, so linears, quadratic, cubics, and quintics. And important, at the boundary of this overlay, we impose a 0 Dirichlet boundary condition, and we add up these levels, meaning that the sum of this is refined in this middle part, and it is continuous, as at the interface, a 0 is added from the overlay. And you can do this not only in one layer, you can do it in an arbitrary number of layers. You can play this game also in 2 dimensions, and well, there is you can even get exponential rate of convergence, and you have very powerful adaptation. But what about really programming it in 4 dimensions? Well, how can you do it? We start with a P version of the finite elements, and now I come a little bit technical, but I will try to show that there is a data structure which is extremely and astonishingly simple, so that you can make this adaptation in any spatial dimension. So we are starting with a P version. And well, here is only shown one element, a square, one square element with all its shape functions to define a quadratic ansatz space here. So we have, what do we have? These are non-standard shape functions in a sense. These are integrated Legendres. So the usual ones, the edge modes, H1, H2, corner modes, 4 corners. To these corner modes come in addition edge modes, which are non-zero, only always at one edge. And we have an internal mode, which is this one. So these are the 9 shape functions which are defined for a quadratic element. Okay, so imposing 0 Dirichlet boundary conditions, this is something which is trivial, and this is a key issue for this adaptivity. So what can we do? Well, if this top side is put to 0 Dirichlet boundary condition, the top side of the element, then we just deactivate these 3 shape functions. So this corner mode, and this edge mode. If we deactivate on the right side the shape functions, then we impose a 0 boundary condition on the right side of the element. Well, we can also deactivate 6 of the 9, then we only have these 3 shape functions, which are shown here. So activation and deactivation of shape functions means imposing boundary conditions or activating or deactivating degrees of freedom. So this is the key idea. And you can play this game now also in a hierarchical way. I show the idea on this simple 4-element basic mesh. We start with polynomial degree p = 1. We try now to make an approximation, and this is an HP approximation. So, well, if you look at this mesh, then you have something which is a hanging node here, and you have polynomial degree p = 2 and p = 1. So what are the standard approaches? So this is not the hierarchical. What is the standard approach? We have to deactivate shape functions at these hanging nodes, meaning, well, if we have on the large element a quadratic shape function here, and on the smaller elements we have the linears and these quadratic ones, well, then we need to do something. Looking at these 4, 1, 2, 3, 4, and 5 shape functions, then we need to get continuity, meaning that what is on these elements is composed of this shape function, this, and this one. So we need a combination A, B, C, and D, so that the continuity is guaranteed. Well, this results in a small system of linear equations to get these coefficients. So this is possible, and this is done in many of the HP codes, which are in some research implementations around. Well, the problem, if you want to implement this in 4 dimensions, I would say at least that it is very ambitious. I would even consider it as impossible in practice. Now let's look at the other approach, this hierarchical approach. This is again our mesh, which we are having, but this is composed out of 2 parts. A base mesh, and an overlay mesh in this hierarchy. And now I define first, well, I look at the shape functions which are defined on the base mesh, and for this one I define the quadratic ones in the right or lower element and the linear ones in the left elements, which are, and in this upper elements, which are below the overlay. So this was the definition of all the shape functions on the lower level. Now let's look at the higher level. So what is the activated set of shape functions? Well, remember, on the overlay, we choose only p's equal 1 for simplicity. You could choose any other polynomial degree. It might be higher than on the lower level. It may be the same. It may be lower. And this is what we are having here. So we have this shape function, and this is one which we want to keep in our ansatz space. This shape function, the same, and different to this shape function. Look at this. What is different to this shape function from the one which we had before? Well, it's exactly this edge of the element, which is a connection to the lower hierarchy. And if you remember, the trick in this hierarchy is that I say, well, along all this boundary, which is connecting to the lower level in the interior, I impose 0 boundary conditions. Well, 0 boundary conditions mean I do not take this shape function. I just deactivate it. Well, let's look at further shape functions. The one back there has no interior connection to the lower level. The same for this one. This one, again, has a connection along this full edge and is deactivated. Not deactivated, this one. Not this is active. This is non-active, deactivated, and important also in this element which is in the corner back there. And well, in this way it goes on, and we activate or deactivate shape functions on and on in this way, and do this for all levels of hierarchy. Well, I promised the data structure, and this is something which is astonishingly simple. What we are using is a d-dimensional array of Boolean variables. So this is a tensor product mass to trace or to track active functions. D-dimensional means in 2 dimensions. I have a 2-dimensional Boolean template. And now let's look at the equivalence of the activation, deactivation, and the template. So these are my shape functions, deactivated, meaning in the template, I have 3 zeros on the top row. So edge mode, a corner mode, edge mode. The others are active. If I'm on the right side, again, deactive in the template in this tensor product mass. If only the lower would be active, I have only the ones in the lower row of the tensor product mass. And this translates now to the hierarchy. So what are the steps? In the first step, I activate all shape functions which are on the lower level, and on the higher level, the leaf elements. Well, what are leaf elements? These are, if I look from the top, these are all the elements which I see and where I want to loop over my element matrices. Well, activated first everything. Now I need to adapt these templates which are there. First thing, I need to extend the template which are here to those which are in the neighboring parts where an overlay exists. First, 0 everywhere, but this would not give me a continuity. Remember, the continuity is obtained by having along one edge the same shape functions on the same level as on the neighboring edge. So I activate these, meaning just I reflect the shape functions here over this edge. the same up there. Well, there is still one shape function which is connected in the upper left element to these two, which is deactivated. So still an activation over this edge here, and now everything on the lower level is as it should be and defines exactly the shape functions which I need to have. Well, let's go to the next level. First step is I need to deactivate to get the zero boundary conditions. Deactivate along this edge and this, and on the upper layer means that I put zeros in the templates along these two edges and in these elements. I'm still not ready because there is this one shape function which needs to be deactivated, and just by reflecting over this corner. Well, and that's it. Now I have defined all active and deactivated and deactive shape functions on these two layers, and I do this exactly in the same way on all layers for all polynomial degrees, and well, we can do this in any spatial dimension. This is the important advantage of this data structure. Well, now let me come back to the heat equation. And now we will see that it really works in 4 dimensions. The heat equation is now considered in the non-dimensional, non-linear setting. So I have a volumetric heat source. I have a phase change function, which defines, I don't want to go into the details, it defines a non-linear heat capacity, a heat conductivity with, this is a phenomenological model which is used by such a phase change function which we are having here. And again, space-time Petrov-Galerkin formulation, which is non-linear now in this case. So this goes back actually to 1989 to a publication of Assis and Monk in this case. So the linearization needs a discrete weak residual, and in the Newton method we solve this in this time-space Petrov-Galerkin formulation. Over integration in the elements where the phase change exists, and the bisection start of the algorithm to improve the update. We start with a smoothing factor to get a good initial guess in this 4-dimensional Newton finite element method. Okay, let's come back to the problems which I showed you already at the beginning. Parameters are adjusted exactly as they are defined in this benchmark problem. I start this 3-dimensional spatial problem, 1 dimension in time, with a base mesh of 12 by 12 by 2 elements and 8 elements, 8 slabs in time, and uses a p degree, p is equal 4. So this is quite a high p degree, so high accuracy. And well, this you saw this video already at the beginning, comparing experiment and computation with the parameters which we have adjusted here. You see a very good agreement in this this table concerning the cross section and also concerning length and width of the view. Now let's look at this hatched square which we are having. And well, now you see the laser running first around and then hatching in the diagonal. And what is important, you see the spatial adaptation. And on the right side up, you see the slab. So this is the time adaptation which you are having. So that you can see in this cut, it's really 3-dimensional. So you get a refinement and de-refinement also in the depth direction of this structure. Okay, so well, what you see here, this would be in real time. So this is the process for this is really about 6 seconds. The computation time, and this is still on powerful workstation, I would say, one CPU, is still in the order of 10 to 15 hours. So still quite a significant time which we are having here for this problem. But, and as I said, it's work in progress. We are going now to real high performance computing, where we expect that we come down to, well, minutes for this simulation, where really the physics is resolved in this scale from melt pool to the layer. Okay, so now I will go very quickly to the last part of my presentation. I do not want, I will not make it in 1 minute, maybe it is surely a little bit more, the application area of viscoelastic layers, which I address. This is motivated here by an MRT, which is layered on a bearing, which is, a really interesting construction concerning a possibility of application of additive manufacturing in a composed way. Actually, we have first printed parts with our colleagues in the mechanical engineering department in Munich. So this is a first part of the lattice, which is the core of this viscoelastic layer. Well, we are using immersed boundary methods to simulate this this composed structure, and these immersed boundary methods, I've talked about this very frequently. I give only the general idea. So we embed a structure, and this may be complex, into a larger one, complex geometry into a larger one, get a simple geometry which is meshed in a simple grid. And in addition to this, we have an indicator function which tells us what is inside and what is outside the domain of computation. So this translates to a formulation on this extended or immersed domain with this indicator function. So these immersed boundary methods have, of course, a lot of problems to be solved. So we have cut cells, which are characterized by the boundary going through these cells or elements. We need to find efficient and accurate ways to define boundary conditions. We have to solve stability and conditioning issues in case of small cut cells. And we also have, of course, to have local refinement. But what is important, this can all be used in exactly the same way as I showed it, just in this space-time approach. Local refinement in 4 dimensions is possible also for these immersed boundary methods. There are several variants around. I use, and we are using in Munich, the so-called finite cell method, which is high order in time and space, and high order with a local refinement, hierarchical, in the way how I showed it you in the first part of my presentation. What is interesting for these structures, which are important here for these viscoelastic dampers, is that we can use multiple geometric models, and in particular geometric models which are very well connected to parametric design, parametric CAD design for these basic cells for these dampers. Well, the viscoelastic material which we are using is a linear viscoelastic material, which is described by a complex constitutive equation. So what is changing essentially is that instead of a real valued elasticity modulus, we have in this case a complex modulus, and loss factor, which is a measure for the viscoelasticity which we are having here, the loss factor is related to the materials which we use as components of this connection. So the elastomers or polymers and metals, which we are combining in a stiff lattice and a lossy material matrix. Well, if you look to this, then the stiff lattice is something which is in a sense ideal to be manufactured by AM. The lossy matrix is then just filled in, and the structure which we are using is one which was defined by Andreasen and Sigmundsen in a publication in 2014 by topology optimization. Essentially, they got it in this way. And the material of the combined structure is something which is composed, well, in the microscopic scale out of these two types of structures which we are having. On the macroscopic scale, we are obtaining it by computational homogenization. This homogenization approach means that on the micro scale, we use, well, essentially virtual test cases. In this case, it's 6 linear independent load cases, and from these, by local computation and by an integration and averaging, we obtain macroscopic material properties. Well, the model of the microscopic structure is a parametric computational structural geometry model, and well, the geometric properties is this alpha strut and this alpha gap, which are here. And we have now the goal to define the properties with the finite cell computation, the properties for a large variety of combination of these parameters. We embed each of these parameters in a completely automatic way and couple the lattice with the matrix and get finally for these large set of parameters. And I just would like to show the principle what we are having here. We have a large number of computations for all these parameters and get these tables or these diagrams where now from an engineering point of view, it is possible to find out what is the right combination of material, the right combination of the geometric properties to get certain combinations of material parameters in this composed part. Okay, so last 2 or 3 slides, we embed now this structure, this damping structure in a larger one. Take this viscoelastic layer as a damper in the large part, and then we are studying different types of coupling the large parts with this microstructure. Well, one type is really to make a detailed computation on these different levels. This is possible, but leads to a large number of degrees of freedom. Another possibility is to use a mortar type simulation, a mortar type coupling of these combinations, and well, showing just the results. And I go to my last slide to come to the end of my presentation. If you want to look now to the frequency response, so this is what is interesting from the application, from the engineering point of view. So this is a large scan of frequencies with many, many parametric computations, assumed part of it. So you see a cut through this structure in the different numerical settings. So we have a fully resolved with several millions of degrees of freedom as we go from the micro to the macro scale, or this homogenized approach with much less degrees of freedom, and even less if we have this mortar-based approach, you see that these results are very similar in the size of the loss factor, and looking at the scale, also very close together in the frequencies. Well, I come to the end of my presentation. I tried to show you in particular a possibility for space-time finite elements, which seem to be very attractive for these spatial temporal problems which we have in additive manufacturing. And I also tried to show you that the finite cell method gives the possibility in particular to make computations which are adapted to a parametric approach, which we are having here in these applications. So thanks a lot for your attention, and sorry to be a bit over time, but I hope that at least with the second start, the PowerPoint presentation worked in the right way.
Thank you very much, Ernest. Really, thanks. Thank you very much, and very deep presentation. So you say you were going to talk only about challenge of scales, but in reality, you especially in the second part, you address also many other subject and very, very interesting points. I should say that I recall, I don't remember where, but I clearly recall quite a few years ago that we were just at the beginning of our discussion on additive manufacturing, and we were discussing about the issue of scales. So after many years, we are still struggling with this aspect, but I really think that this is also the beauty of this manufacturing technology that's posing really many challenges from the practical point of view, but also from the computational point of view. So thanks for this very inspiring lecture and many points that you raised. I would open the presentation for questions or comments. Is there, so everyone that wants to pose a question should turn on the microphone and ask the question.
Hello.
Michele, please.
Hello, thank you.
Hello, Michele.
Hello, Ernest. Thank you very much for the presentation. I apologize, but I didn't catch completely how it worked, the space-time. I think I need more time to digest this stuff. But any case, I cannot see any way how to deal with the historical variable. Meaning, if a part of being nonlinear, you have any kind of historical variable, being this historical variable, I don't know, microstructure evolution or plasticity, what happened with the space-time? I don't think it's possible, isn't it?
Okay, if you really have historical variables, I think you are true. So the nonlinearity which I addressed here in this talk was not historical. So you can formulate in this way as one slab.
Yeah.
Okay. Otherwise, if you have historical variables, the question is how big are your slabs? You can make for sure slabs which are much larger than only one time step. This would then mean, if you have historical variables, that you make the update of the historical variables only after several time steps if you talk in the usual way on time steps. That would be a possibility. In this sense, you get larger problems, but on the cost that you do not update the historical variables in every what you would have as time step in the method of lines.
Yeah, okay, but this means that you lose a lot of the accuracy of the, let's say, the plasticity or whatever.
Okay, yeah, but well, you must consider it. What is the alternative? One alternative is, for example, that you make one layer as a whole, yeah, then you would make the update for one layer. So this gives you, if you do it in this way, this gives you the opportunity to play with all the intermediate possibilities. Yeah? So update of the history variables after, well, the number of time steps which you consider as possible, which may be much, much less than what you would get only for one layer or for one stroke.
Okay. I would like to, but next time, I would like to see just the same small example of the one stroke with plasticity. I don't know, just to see what happens in just this one stroke. If you go from the beginning to the end of the strokes and you update the historical variable, it's not clear to me what is going on.
Okay, so well, to make it clear, I talked about the problem of the temperature, yeah, and not the mechanical part of the problem.
Yeah, but you can think about, I don't know, microstructure evolution, anything that has an historical variable, anything that depends on time.
Yeah, as I said, of course, you would have, you would not make it in one stroke, in one time slab. Yeah, so this is exactly also what we did in this case. It was not one time slab. So for this one stroke in the benchmark problem, we had 8 time slabs already there.
Okay. Okay, thank you very much.
Thanks. Any other questions or comments? Okay. I see Stefan turn on the microphone, but I don't know if you have a question. I mean, you're supposed to know everything. Oh no, okay. Okay. I have a very small question. It's more a detail. Ernst, at a certain point you show 2 weak forms. One was with the weight function. The other one was with the derivative of the weight function. So you're using, it's like you're using 2 different weight functions, or what is the main differences between the two? It's just the fact.
Okay, well, these are just 2 different possibilities, or 2 different lines. If you look to the literature, then you find these 2 variants. There's the second one, the one with the time derivative. This is supposed to be more stable. So Lange, for example, is also using this one with the time derivative. But we have also experience with the symmetric one, with the Bubnov-Galerkin. This works reasonably well, but it is, as I think it is not possible at the moment to give a mathematical proof of convergence for this one.
Okay. Okay, thank you very much.
So if you look to the results, and actually we have, as I said, we have both implementations. For this example, which I showed, you do not really see differences in these 2 possibilities. Of course, you have a different implementation.
Okay, okay, thanks. Any other comment or questions, or? Well, if not, I mean, since we, we are almost at the end of the time slot that we consider. So I would really to thank Ernst for your presentation. The presentation will be available also on YouTube. I can say that there are also people already attending on YouTube, and among others, I got an email from Bob Taylor that was attending your presentation on YouTube. So thanks very much, Ernst, and thanks for everyone for showing up, and we'll send you